In a world where technology becomes obsolete in the blink of an eye, NASA's reliance on a software engineer versed in decades-old programming languages for the Voyager spacecraft is a tale of remarkable technological endurance. But how does one manage and update a space probe software from billions of miles away? Stay tuned to uncover the remarkable process of keeping the Voyager spacecraft operational, a feat of enduring space engineering. Back in 2015, NASA issued a job advertisement searching for a software engineer with a unique skill set. They required expertise in FORTRAN and Assembly, two programming languages dating back to the 1940s and 1950s, which are unfamiliar to most recent graduates. The purpose of this recruitment was to enlist a professional to join the exceptionally small group of individuals dedicated to the Voyager space probes. Remarkably, both Voyager spacecrafts continue to operate on their original half-a-century-old computers, equipped with a mere 70 kilobytes of memory. Although this may seem insufficient, it proved adequate for guiding these probes through our solar system and enabling them to make remarkable discoveries during their journeys. As anticipated, Voyager's computers occasionally encounter issues. Just recently, Voyager 1 started transmitting distorted telemetry data related to its spatial orientation. Additionally, the thrusters responsible for maintaining Voyager's proper alignment began displaying signs of wear and tear. Each time the thrusters are activated, tiny particles of hydrazine fuel become lodged in the pipes, leading to gradual obstructions within the system. Voyager has already transitioned to its backup thrusters, and should they fail, it would spell the end for this pioneering spacecraft. Situated a staggering 15 billion miles away, it is impossible to physically clear the tubes. Nevertheless, to mitigate the accumulation and resolve the telemetry problem, the small team overseeing Voyager's operations embarked on developing a software upgrade that would traverse the expanse of our universe to rectify these issues. Voyager boasts a trio of primary computers nestled within its spacecraft. The central computer assumes the role of overseeing all critical instruments, managing its own well-being and temperature, and simultaneously governing the other two computers. The second computer takes charge of Voyager's orientation, diligently seeking predetermined reference points and activating the thrusters to ensure that Voyager's antenna remains aligned with Earth. The third computer is tasked with the vital responsibility of storing and managing the extensive scientific data and images captured by Voyager's instruments. It's worth noting that Voyager operates without an operating system, as any programming language would consume an excessive amount of valuable space. Nevertheless, Voyager has undergone software updates before. During its encounter with Neptune, where the ambient light was a mere 900 times dimmer than that on Earth, engineers found it necessary to reprogram the camera to capture longer exposures. Subsequent to its departure from Neptune, NASA initiated the deactivation of certain components, such as the camera and various scientific instruments, to conserve power. Given the meager 70 kilobytes of memory available on Voyager's onboard computer, dedicating lines of code to inactive instruments proved impractical. Consequently, engineers opted for a complete rewrite of Voyager's code, conducting a software update to ensure its continued functionality in the foreseeable future. However, the question remains, how does NASA undertake the formidable task of updating such antiquated hardware from a distance of 15 billion miles? To grasp the complexity of this challenge, it is imperative to delve into the intricacies of Voyager's software. To execute a software update on Voyager, NASA must implant the new code into its computer systems. One of the most fascinating aspects of Voyager's computers is their memory structure. Each computer is equipped with its own plated wire memory, where Voyager's code is stored in its most elemental form, binary ones and zeros. This memory framework comprises a physical grid of wires and delicate metal plates. Every intersection point serves as a singular memory bit, capable of holding either a 1 or a 0. The manipulation of this memory occurs by passing a current through a specific wire and plate, generating a magnetic field. When the magnetic field aligns in one direction, it registers as a 0. Conversely, if it goes in the opposite direction, it signifies a 1. By altering the current's direction, the bit can be flipped from one state to the other. This process is repeated for each point, enabling the storage of the binary data. This design was a wise choice in its time, as it guaranteed the preservation of ones and zeros even in the event of a power outage. Furthermore, it allowed for individual bits to be updated. Voyager's limited memory capacity, a mere 70 kilobytes in total, necessitates an exceptionally efficient approach to coding by the engineers. In addition to the fundamental machine code, Voyager employs its proprietary pseudocode, an array of concise commands designed to automate repetitive tasks without consuming excessive memory. An interpreter within the main computer reads the binary data, and upon encountering a predefined code, it triggers the corresponding pseudocode command. This approach not only conserves memory, but also facilitates the automation of numerous tasks without the need for extensive lines of code. However, the challenge lies in the fact that humans cannot compose code using just binary ones and zeros. Consequently, a more advanced programming language is essential to create the code that operates Voyager effectively. Back on Earth, the software for Voyager was initially crafted using assembly language with a sprinkling of FORTRAN. Assembly is a relatively simple programming language that can be comprehended by humans, but is much closer to the fundamental binary code of ones and zeros, akin to machine language. Once the code is fully developed, it undergoes a compilation process, transforming it into machine code. This compiled code is then transmitted to Voyager via the Deep Space Network. Remarkably, data transmission to Voyager occurs at a rate of a mere 16 bits per second, taking nearly an entire day to traverse the vast distance and reach its intended destination. Voyager's onboard computers operate in an interrupt-driven fashion. In essence, the software follows its typical sequence of instructions until an interruption occurs. When an update is dispatched to Voyager, it carries with it an interrupt signal. Upon receiving this signal, Voyager instructs its main computer to halt its ongoing tasks and focus on implementing the provided update instructions. Subsequently, the new code is loaded into the memory, causing the binary bits to be rearranged according to their new configuration. A thorough code validation process is then executed to ensure correctness, after which the main computer resumes normal operations, effectively integrating the update. Throughout its mission, Voyager has been the recipient of an extensive catalog of updates and patches aimed at rectifying issues and enhancing its operational capabilities. In 1995, an update was developed with the primary purpose of essentially restarting specific components should they encounter failures. In 2014, a remarkable 2 decades after the initial code was written, this very code proved to be the savior of Voyager 1 when a hardware component malfunctioned. Then, in 2010, a seemingly minor glitch occurred. A single bit within Voyager's memory flipped, transforming a 0 into a 1. This seemingly inconsequential event led to a loss of synchronization between the spacecraft's computers, resulting in commands being executed 2.5 hours later than scheduled. To rectify this issue, a software update was dispatched to correct the faulty bit, restoring it to its proper configuration. Stories like these underscore the incredible resilience of these iconic space probes, enabling them to endure nearly half a century of exploration in the vast expanse of space. It is truly astonishing that the physical wires, transistors, and hardware within Voyager's computers continue to function as originally intended after all these years. What are your thoughts on the incredible journey of Voyager and the challenges faced in updating its decades-old technology from such a vast distance? Feel free to express your thoughts and viewpoints. And be sure to join the Revel Discovery community by hitting that subscribe button to stay up to date with lunar revelations and the forthcoming frontier of space exploration. Remember, as we venture into the universe, the sky is not the limit, it's just the beginning. Keep looking up.